Hey Emily, so I randomly forgot to start recording at the beginning of class, but they worked out this example the first time. They got a little stuck in the simplifying, but they were able to finish. So if you want, you can go ahead and just start trying to solve the problem, then check it. We talked about the chain rule just a little bit, talked about differential notation, about how dy dx gets broken down with the chain rule. You're taking the derivative of y with respect to u, then derivative of u with respect to x. It goes along with this notation. We're going to get back to this when we talk about parametric and polar. Then I had them work this one out, which we figured out at the end it would have been probably easier if we had just plugged in for the u and solved for the derivative this way and gotten 1. You could have also solved it, though, with the definition of the chain rule. And now they're all going crazy because I gave them this problem and I'm not paying attention to them, so they're all distracted. All right, here we go.
They just roasted us.
Please get back to dumbbells.
Okay. All right, cool kids. What was the very first? What's the outer?
Cube root of u.
Cubed root. What's the next matryoshka?
Negative cosine of 3x.
Not quite.
Turns to 0.
What's the next inner?
3x.
Did you get them all?
Yeah.
So then, f prime should be. Don't tell me to simplify. Tell me step by step. What's the derivative of the outer?
Bring down the third.
1/3.
Uh-huh.
Negative, and then to the negative.
The cube root. Or not 1. 2/3.
I said 2/3.
Okay, times what?
Inside.
Negative side.
Times sine of
3x.
Yes, Alan, you're right. I'm just doing it step by
Minus
step.
3's canceled.
True, the 3's do reduce. And you end up with sine of 3x all over the cube root of
17 is
dun, 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 dun.
You didn't have to put on the bottom. No, in the square root. Oh, you could do that. I did.
You could. I'm not sure if it's going to actually simplify it. You will have a cosine squared, but you'll also have a cosine. You won't be able to get all the way back to sine.
Let's find the second.
Ooh, let's go.
No. Trying to kill us all.
I didn't say it. Jonathan did. Pause. Let's just do them quick together. So, what would you guys do for number 1?
Are you going to do business?
Product.
Okay, true, but what would you do with the 9?
Take it out.
Take it out. Completely.
Get the phone put away, please.
Just leave it.
Yeah, you just leave it, and then
And then you second go first.
second be first.
Second.
Cosine
Cosine of 5x. Times 2. Sine of 2.
Times 2.
No, she already did
Wait,
that.
what?
She already did that.
Sine 2x.
Plus sine 2x.
Sine of 2x and 5 times 2x.
Oh, it's negative. It's negative.
Negative.
Okay, simplify with trig properties.
Yes.
Okay,
No.
double angle.
Oh my goodness.
Double
please
angle.
don't do
Just kidding, alright.
No, I think
You could have done composite argument. You could have done cosine of 3x plus 2x and sine of 3x plus 2x. And
Cosine of 5x.
let's see, cosine with or together. Cosine, sine. Cosine, sines change. Remember this from pre-calc?
Yes.
No.
So it's
Wait,
5x minus.
You guys don't remember cosine of a plus b?
No. 5x minus 2x, right?
Oh, is cosine A
You know nothing,
cosine
Jon
B
Snow?
plus sine.
Cosine, sines change.
Yeah. You got killed by the little guy who killed Jon Snow.
I remember
Sine.
this. And then-
Anyway, we could have gotten 3x plus 2x, but we still would have a 3x. We could make 3x 2x plus 1x, but still a 1x.
Oh.
We wouldn't have gotten them all to 2x's. Okay, so we'll go ahead and box it and be done. Question. You guys good on the next one?
Yes.
Okay, what would you do?
Make it 1/2. Yeah. Make the square root
Okay, so we can make it to the 1/2 power. Now what?
Do the chain. The chain rule, the whole thing. The whole 1 plus tangent squared 2x on the inside.
Yeah, so then when we take the derivative of 1, it's just 0. Derivative of tangent squared, 2x.
2 tangent 2x.
2 tangent 2x.
Times secant squared 2x. Times
Woo!
Wow, that was like
Not too shabby, right?
it's deep.
How the heck does it go to
So we bring down to 1/2, negative 1/2.
Oh.
Then derivative of the inside, remember, don't get tricked by the trig notation. It's tangent squared, bring down the 2.
This says
Derivative of tangent, secant squared, derivative of 2x. Got it? Am I sticking it to the man?
Yes.
No.
Okay,
Don't.
they're-
It's
they're-
multiple
they're-
choice.
they're
It's
definitely-
multiple
it's-
choice.
it's multiple choice.
For multiple choice, guys, think about it. How much would you be able to simplify? Could you make secant squared 1 over cosine squared? Tangent sine over cosine, but the cosines don't care.
There's not much to do.
Cosine squared.
Secant squared could become 1 plus tangent squared. So you could have it all in terms of tangent. But you can't square root the denominator, so is there really that much simplifying to do? No. But that takes skill to be able to say, right?
Yeah.
That takes skill to be able to say. Alright, cool kids. Ooh. Parametric equations. So, what do we do? What do we do if we have, oh, maybe I shouldn't have left him. I thought I was going to leave him. I'll take him off for a second. Parametric equations. We know we have an x of t and a y of t. And if we were to take the derivative of y, does it make sense that dy dt would equal dy dx times dx dt? Does that make sense?
Yeah.
From chain rule. You take the derivative of the y with respect to some other variable x. Then you take the derivative of the x with respect to t. But we're not normally trying to find dy dt, and if we are, we probably can just take the derivative of this guy. Who is it that we're going to be interested in solving for? dy dt would be the rate of y with respect to time. Dy dx would be the slope of the tangent line of the path, the parametric path that the object is moving on. So dy dx from that chain rule up above, which is basically an application of just normal chain rule that we were talking about, how would you solve for dy dx? You would just divide, right? Take dx dt to the other side. So you have dy dt all over dx dt. Now, is there a simpler way of writing this stuff? Yeah, you can do ddt of y over ddt of x. But this is taking the derivative of x with respect to t. If I start flipping, I might get in trouble. Remember, these aren't necessarily fractions, they're derivatives. So instead, how about this? How about y prime of t over x prime of t? Is that a little bit easier?
Yeah.
This is new though, right? This is quotient rule. This is an application of the chain rule to parametric equations. So if we have two separate equations put together, which makes a parametric curve, like you guys did with orientation on the polar parametric quiz, remember that the paths can be like curved, they can be circular, they can be hyperbolic, they can be functions, they can be not functions. If I want to find the slope of the tangent line, or if I want to find the slope at a point on the curve, I can't just take just x prime, I can't just take y prime, because they are combined to make that curve. Instead, I need to basically use this application of chain rule to say, hey, to take the derivative to find the slope of the tangent line to that parametric curve, I just do y prime over x prime. Now, what's going on with the bottom one? The second derivative. Does it make sense? The second derivative, you're going to have to take the derivative of the first derivative. Does that part make sense?
Yeah.
And it's in terms of t, so it makes sense to be ddt, right? But what's a little weird? Why are you dividing by another x prime? I get to taking ddt of the first derivative, but why divide again? Because if you think about it, if you multiply this guy on the other side, isn't he really just a u from taking the second derivative? What was dx dt right here? What was he? He was the x prime or the u prime from chain rule to begin with. This guy, he's also a u prime or an x prime from taking the derivative again. He's also an x prime or a u prime from taking the derivative again, because when you go to take a second derivative of dy dx, you're taking the derivative with respect to t, which is like taking the derivative with respect to x of u's. The variables don't match. And when the variables don't match, you need to have a u prime. So think of it this way. I'm going to put this kind of off to the side. If I was to take d dt of dy dx, does it make sense? It would be d squared y over dx squared times u prime dx dt. Because this is in terms of t. If I'm taking a derivative with respect to x, I'm taking a derivative of the y with respect to the t. But I also have the x in there. I need my x prime, I need my u prime. But our equation says, oh hey, so to solve this guy, you need to do this guy and then divide by 3. Dx dt. So ultimately, these equations are completely dependent on the chain rule. It's kind of hard to see. And yet, that's ultimately where both of them come from. I'm going to go ahead and erase this. And kiddos, ooh, I'm getting out a yellow box.
First, forever, and
Is it just an ever?
Endeavor, yeah. Because the forevers are what you already should have and should be carrying around.
Oh, you want to carry those around too?
Yep.
Hey, Gabby, it's been 3 weeks. I know.
This is an endeavor. However, I think there was an endeavor I wanted from polar parametric. We just never made it, and I never went back to it.
Will this be number 1 or number
Go
2?
team. This will be number 2. I'm going back to get the polar parametric real fast.
Twice a day? Why didn't you tell me that 2 weeks ago? Because I didn't think we'd have an endeavor this quickly.
You guys have it, right? Sorry, was anybody still writing? I apologize. Here it is. Anybody still writing? This is endeavor number 2. I'm going back to find endeavor number 1. But as I do, hey kiddos, thanks for all the excitement, but shush. It was from polar and parametric. I'm going to actually go back and find it. But as I do, can you guys use the endeavor? Ready, set?
Yeah.
Go. Ready, set? Go. Emily, go ahead and pause me now because I'm going to go ahead and go find the other endeavor for them. So first of all, I did put the forever cards in your class notes from last year so that you guys can see them. That's just in CalcBC, your class notes. But also the first endeavor card from polar and parametric. It should be in your notes wherever we put the triangle. It's the triangle and the special formulas. That's the endeavor number 1. Endeavor number 2 is going to be our first and second derivatives of parametric. Okay, you guys figured it out okay? It'll be on the video also if you guys want to see it. Okay, let's go see. That's okay, it's to get used to. So, what's the 4? Really? That's impressive. Here we go. Let's figure out which one's right. To find dy dx. Here we go. To find dy dx, you go ahead and just think of y prime over x prime. That's the easy way of thinking about it. Y prime ended up being, hopefully, 4t cubed minus 6t squared. True?
Yes.
All over x prime was 2t. Now to make our life easier, because in a second, you guys look, we're going to have to find a second derivative, which means we're going to have to take the derivative of this guy. Why not just simplify it, right? That would make life a lot easier. You could do the heart method, or you could multiply this whole numerator by 1 over 2t. You would end up with 2t squared minus 3t. True? Okay. So then we're taking the derivative of 2t squared minus 3t, but careful, I have to divide by x prime. I have to divide by dx dt, which is 2t. The derivative of the top is 4t minus 3. Is that one representation? Yes, that's one representation. But what are we still supposed to do? Good. 4 minus 1? 1 over 2? Okay. What does this tell me about the parametric curve when t equals 1? No, not the slope. What? No. No, the second derivative isn't slope. If I wanted slope, what would I have had to have done? Plug into the first derivative, right? So if I had plugged in 1 to the first, 2 minus 3 would be negative 1. Question, what is my parametric curve doing when t equals 1? It's decreasing. When t equals 1, the curve is decreasing and it's concave up. Curve is decreasing and concave up, right? Does that make sense? First derivative is negative, second derivative is positive, and more specifically, when t equals 1, x equals 0, y equals negative 1, and the curve is decreasing and concave. Nope. Thank you. Second derivative is positive. Now, for my physics people, parametric equations is two-dimensional motion, right?
No, we only have one-dimensional motion. Yeah, they're
Parametric equations is two-dimensional motion. If I was just to plug into y prime of 1 would be negative 2. So question, vertically, what's it doing? Going down. And horizontally plug in 1? X prime is positive, going to the right. So it's going down and to the right specifically. Well, it's headed that direction, but it's not necessarily in the fourth, it's just going that direction.
Yes.
That would be like the vector motion of where it's headed.
So when you put the d squared y over dx squared, and you have to take the derivative, you just take the derivative of top and the bottom, you don't use the
You're right. You're taking the derivative of the first derivative, dividing by dx dt, which is ultimately from 2.
So you don't need to use the quotient.
No. Well, I mean, if this was a quotient, you have to use the quotient rule there, but then just a strict division by x.
Alright.
Yeah. That's why I need you guys to memorize the card, because it doesn't necessarily, like, it does follow, like, it does make sense, but it's probably going to be easier just to memorize. Where are we at? The end of class, I know that. Oh, whew, good.
No.
Section 4.1, due tomorrow.
Miss D, can we have a pardon?
A pardon?
Because
Party?
no, pardon. Because there's calc correction, so maybe we could just squeeze it for Monday. The corrections are supposed to be.
Who else needs correction papers?
One's correction.
Correct, those are due tomorrow.
Gordon's
Cameron, spirals done, chapter 2 and 3?
I didn't need one to see.
Not done? Okay. If you need your spirals, wait, pass it to Court. Who else needs correction papers? Pass that to Lucy. Who else needs correction papers? Guys, it's enough. How many of you still need to work on corrections tonight? corrections are due tomorrow. Homework 10 is due on Monday, but you might have a homework 11 also. So if you want to pick up your spiral today, I'll try to have it done by the end of the day. But is there pressure to pick up your spiral? No, not unless.
Hey Noah.
Not unless.
Hours?
Not unless your chapter 2 is in your spiral. Go get it. Because you can't do corrections if you don't have it. Go get your chapter 2 test if you need it for corrections. Otherwise, you're good.
Time to go to my favorite Bible teacher ever, Mr. Williams.
Go get your chapter 2 test.